Well, I have an introduction. This is, and I'm going to. So I've been speaking to Leif this whole afternoon, and he's I think the word is polyglot, a speaker of many languages, including talking about when he spent time as a visiting professor in Japan and giving his talk about what physicists do. He was remarking. In Japanese, so I was very impressed, and so I'm a little embarrassed that pronouncing a name which is basically from my heritage could be problematic, but it shouldn't be. His name should be very, very straightforward to me, which is, as we said, Leif.
Yes.
Svalgaard. Not exactly right.
But close enough for government work. So.
Oh, thank you. I appreciate it. Thank you so much. His graduate study was at the University of Copenhagen, and his work, I just have to tell this story, which is for a class recently. I sat down and listed all the computer languages I've worked with in my life, which is numbers over 20. So you sort of talk about, oh, what's the new language of the day? And in looking at Leif's academic history, he did some amazing programming work in 2 languages not amongst my 22 languages. He worked in COBOL and ALGOL, which of course I've heard of, and those of us of a certain vintage will have known those languages. But very impressive work, early work in coding in geophysics, so doing meteorological map making, in some ways early sort of depictions of weather phenomenon visually through the computer. He went on to, in 1972, go to Stanford and work in space physics, helping form the, I don't know if that was, you helped him form the Institute of Plasma Physics there.
It was there already.
It was there already, but got to work in there. Then took a very interesting turn working for the US as a representative to a Nixon-Brezhnev summit on, is it the environment? So very interesting work between the US and USSR at the time. And then went into the private sector, which I learned this afternoon was for family reasons, going into the private sector, working in Europe, working for a variety of industries. Well, in the United States, he had worked at Lockheed and New York Directory Assistance. I thought that was fascinating. But
it was.
And then he went into work, and that was mostly in military communications while in Europe. But then returned to space physics and to research in 2002, and is working with the Stanford Solar Group on the portion of the Solar Dynamic Observatory called HSI, or the HMI, Helioseismic Magnetic Imager. We're very pleased, and let's give a warm welcome to Dr. Leif Svalgaard. Oh.
You're better than the Japanese, because when they say my name, it comes out Raifu Superrugado. And I learned the hard way that that's me. Okay, I have chosen this title because we live on the Earth, so the sun's effect and influence on the Earth is important to us. And this is a huge subject. Of course, I cannot do justice to it in a little less than an hour. So you'll get more or less my personal feel for that. Ooh, I'm supposed to have this thing here, but this also works, huh? Right. So let's start looking at some of the regions of the sun. Most of you probably know that the sun has a very hot core where thermonuclear reactions convert hydrogen into helium and send out neutrinos, which we can pick up on the Earth. In fact, every second or so, about 1,000 of them pass through my thumbnail here, just like that. Then, as you go outside from the core, there's a zone here which is called the radiative zone. Their transport of energy is by radiation, and the density is so high that it takes a photon 250,000 years to make the journey from here to here. It is of course not the same photon. It is absorbed and another one emitted, and so on. But finally, when it gets to here, then convection is the most important, most efficient way of making transport of energy. And Mother Nature always is cheap. It takes the most efficient, the cheapest way. And so here it takes about a month for the energy to get to the surface, and from there another 8 minutes to the Earth. The temperature is very high in here, millions of degrees, falls to about 6,000 Kelvin at the surface, the photosphere, and then increases again to 1 million or more degrees in the corona, which you see here. It's the magnetic field that the sun has that makes it interesting. Without the magnetic field, we would not have all these things, sunspots, prominences. We would probably not have any corona either. And it also sometimes makes the sun dangerous. So my talk will be centered around the magnetic field of the sun, how we measure it, can we see it, what does it do, and so on. Let me trick this one here. So first let me show you how this guy here, this is a sunspot group. We call this an active region. And here you can see this is the time lapse over several days. From about here to here, the sun is rotating. And you can see how it grows. And this is taken, these images are taken by SDO, our Solar Dynamics Observatory, which we'll talk more about later. Now, this is what it looks like in visible light. And these dark things here are, as you know, sunspots. They're not really dark. They're just by contrast, they're dark. If you take the smallest one of these, like this one here, and remove the rest of the sun, just have that guy hanging in the sky, it will shine, that alone, brighter than the full moon. Because this is 4,000 degrees Kelvin, so it is hot, hot, hot. It's only by contrast that it looks dark. All right, let's stop this one. What makes a sunspot is magnetic field. And so we have a magnetometer here. That magnetometer measures the magnetic field. White means the magnetic field is sticking out, and black is going back into the sun. You can see how it bubbles up from below and coalesces into concentrations, one here, one there, one there, which of course were the sunspots that you had before. All right. Once, I think I can do this one again. Yeah. Simultaneously with that, once a spot is formed, it also immediately begins to decay. You can see that there, for example, see? Those black and white things streaming away from the spot. So we have a very dynamic thing here, which is why we call it the Solar Dynamics Observatory. And we take a picture there, an image every 45 seconds. And our motto is, all the sun, all the time, because we look at it continuously. We don't have night and day. I'll come back to that later. So we are way out in space. Up in the million-degree corona, we can actually see the magnetic field lines. Normally, you can't see a field line. There are field lines here, but you don't see them. However, if this room was filled with plasma, the ions and the electrons would tend to gyrate, as you know, along the field lines, and so we can see the emission of that plasma. If it's dense enough, and here you basically have like that. You can see those very graceful lines, and some of the time, I'm sure that you know that, this becomes unstable and blows up, and that one there didn't work. So Steve made a nice
mouse on it.
A nice replacement of that. What do I need to do here?
Wiggle on the trackpad till you get the cursor, and then click.
There we go. A miracle of modern technology. Now this is a CME explosion on the sun. Now, it looks very impressive, but you probably know that the solar surface, and you saw that on one of the first movies, is covered by little granules, which is the top of those convection cells. And the amazing thing is that if you take this, and there's about 5 million of those all over the visible disk, so 10 billion over the whole sun. If you take one of those cells and ask how much mass is there in that, one of the teeny tiny cells, it's about the same mass and we have in the biggest CMEs. So those CMEs, as far as mass is concerned and as far as energy is concerned, are teeny tiny. Okay? So sometimes they look very impressive. Here's the biggest one we've ever seen. It's not quite the CME yet, it's a filament. And you can kind of see that it is helical. It's more or less like a slinky dink. And this actually, a few hours later, did erupt. And there's a movie of that which I don't want to play. We've seen one eruption, you've seen them all. The mechanism for that is sketched here, and this picture has not changed in the last 50 years or so. We basically have a magnetic field between two spots, and up here in the chromosphere and lower corona is material that has condensed out of the corona and is kind of hanging in the magnetic field. This is unstable, and sometimes the two legs of those fields, have opposite directions, get moved together, either by those two moving or by the corona fluttering a bit. When that happens, we have magnetic reconnection. We have an exhaust that way and this way, so energy goes out here. That's the CME, goes down here, and dumps its energy in the photosphere. Brightening this one. So we see something happening up here and something happening down here. And here's an example of what happened down here. And there are the two foot points. And here is where the hard X-ray emission is coming from. That's from here. And then this thing here, a flux rope if you like, continues out. And here's one of those, CME. And sometimes when it comes our way, we see it as a so-called halo CME, that is, the thing is all the way around the sun. And we also see radiation coming at the same time. The CME is not radiation, it is mass, ordinary protons. Call it radiation here is something we do for historical reasons. It's not radiation, it is very highly energetic particles as well. They are called radiation for, just like you say, cosmic rays, they're not rays at all. But once a name is established, this stays there. And here's kind of a little overview of some of the things that these things can do. Can damage satellites, we'll come to that. They screw up the ionosphere, so communications are impaired. They can damage transformers, we'll see that. They heat up the upper atmosphere, so that moves up into the path of the satellites, so we get orbital decay from that. They corrode pipelines, they disturb positioning, they disrupt ATMs. Cell phones don't work well. You name it, just about anything in our modern world can be influenced by this. Oops, here we go. Power networks are especially vulnerable. Why is that? Well, what happens when a plasma, a conductor, hits a magnetic field, you get an electric field induced. Okay? And that creates a current if there's enough particles to carry the current. And that current will be induced in power lines, for example. They are long linear conductors. And so power networks here and here are especially vulnerable to that because the voltage simply goes up and then the transformers either burn out like this one or they trip. And of course, if the networks are connected, then if one of those blow out, then it has a domino effect, others blow out and so on. We're down here, so we're probably okay, but it doesn't look too good for the other ones. The problem with the transformers is that they are usually custom made. The big one costs $10 million. They don't have them in stock. It takes 6 months to manufacture a new one. And if all these power companies says, well, I need 200 transformers, can't do it. So that's one of the biggest problems. Now, we have a wonderful system of geostationary satellites out here at 28,000 miles up. And here's my old friend Bill Livingston from Kidd Peak. And he has a camera, you cannot really see it. But with this one, he took a picture. He just pointed it up in the sky. And here's the projection of the Earth's equator up in the sky. These streaks here are, of course, stars, right? As the Earth rotates, and the shutter is open for an hour or two, you get the star there. But those points here don't move, they're stationary. They stay fixed. Here, you cannot read them, but here are some of the names of those. There are about 650 of them. And our one, Solar Dynamics Observatory, is also one of these, but it's a little bit special. It's out there, so it follows the Earth in its rotation. Why does it do that? Well, it does that because we need to be able to communicate with it. So we have an antenna, our own antenna, in New Mexico. And Satellite 6 just up above that. The predecessor of that satellite was at a place called L1, about 1 million miles towards the sun. And there the signal is so weak that we need one of NASA's big dishes to pick it up. Here an ordinary teeny tiny off-the-shelf antenna can pick that up. And you can it's not a point, it's a streak. I've kind of amplified it here a little bit. Why is that? That's because we are not sitting exactly in the equator. We have an orbit that is inclined about 20 degrees. Why? Because we don't want to be eclipsed by the Earth every day. Right? So by sitting up there only twice a year do we have an eclipse. All the rest of the year we see the sun all the time. Now these are very vulnerable to solar storms. The total investment of that here approaches $500 billion. And many of those will blow up or become inoperable if the storm is big enough. Now, here's the sun. There are stars that have spots, big spots. That's the biggest one that we know. How do we know that stars have spots? Well, this is the sun, and we observe it in calcium-2 light. That's ionized calcium in the ultraviolet. And these things we can see, here is just the total emission over the disk, and you can see the sunspot cycle here. This is 11 years. Here you can see those same or similar cycles in other stars. Right? And by proper computer manipulation, you can make an image. So some stars have spots that are much bigger. And then there's a spacecraft called Kepler. You probably have heard about this one. It sits and stares at the same piece of the sky, watching in parallel almost 150,000 stars all the time, doing nothing else. Doesn't scan or anything. It just sits there, records the light curve or the amount of light we get from each one of those 154,000 stars. And here are some of those light curves. And sometimes there's a huge spike here. That's the flare. And here's plotted the flares we have seen at Kepler, and here on the sun. Up here we have energy, and down here we have either size or in the area, or up here the magnetic flux. There's a relationship between these two, so you can convert between them. The point is that with Kepler we have almost all the points up here, and with the sun we have almost all the points down here. Now this here we can understand, because if this flare is not huge, then we can't see it. So the cutoff at the bottom here is just because the flares are too small. So we don't know how this one continues down. Conversely, of course, with the sun, we do know, but since we don't know the frequency of this, it could be that a big one is very rare, only once in 1,000 years, and we haven't had 1,000 years of observations, so we don't know how this one continues up. The simplest assumption is that those two are really connected more or less like that. Why would the sun be any different from the 104 and 54,000 stars? So assuming that the sun is like the rest, there is a chance that a solar flare might be huge, like 100 or 300 times bigger than the biggest one we have ever seen. And we can then convert that energy into size. So one of the big ones we see with Kepler will make a sunspot group look like that. And that's bad news for this reason, of course. Now, we don't know if the sun is special. We don't think it is. We don't know the frequency of those. One of those could happen tomorrow, or maybe in 10,000 years, or something like that. So it's just like the big asteroid slamming into the Earth. We know it will happen. We don't know when. It's the same thing here. And if one of those happens, it doesn't matter what we do here. So, on the other hand, the Earth will of course survive. It survived for almost for more than 4.5 billion years. So the Earth will still be here. So what are some of the indicators of large solar events? How do we know about those things? And you can of course look at the sun. As Jocke Berra said, you can observe a lot by just watching. So that, and then we see northern light aurorae. When they go to low latitudes, it means the sun we have a solar storm. The geomagnetic field gets very disturbed. Cosmic rays coming from the sun. And in ice cores, we can find traces of things that have happened. So let's look at some of those things. The first solar flare was observed by Richard Carrington in September 1859. He made a drawing of the pair there, the two bright points. And here's one of the bigger ones lately, called the so-called Halloween event. That's what they look like. And there are many flares like that. If you go to lower and lower energy, there's a flare every half hour or so. Go to even lower energy, there may be flares all the time, but just below what we can observe. The biggest ones are visible in white light, and those we see maybe one a year or something like that. Aurora is when a magnetic storm pushes the Earth's magnetosphere such that particles can come in at lower latitudes. And here are when aurora was seen during Carrington's event in 1859. You see here, even down in Havana and further south. And up here, of course, here, these are stations. No aurora were seen here. Anybody guess why? It's daylight. You have to be night in order to see the aurora. Right? But the magnetic storm was there. The biggest one, the lowest latitude aurora we've seen is here in Apia, in the middle of the Pacific Ocean. It reached down to 15 degrees in May 1921. I have a little anecdote to tell there. There's a little town up in Sweden called Karlstad. And they are very progressive. And they had just built a new telephone exchange. And everybody had a phone. Telegraph, telephone lines and so on. And on each street corner was a little alarm box. So if there was something going on, you could shatter the glass, push the button, and a telephone signal will go to the police and fire station and alarm them. Of course, during this storm, people on the street noticed that all the telephone lines in the air were beginning to glow because of the current induced in them. They glowed so much that the telephone exchange caught fire, burned down. Of course, that means that none of those push buttons worked. So you can be so dependent on technology that using that technology to alarm or to notify the authorities may not work. So all these things are connected. Little side thing there. The city council had just a week before that cancelled the insurance, fire insurance, because it was too expensive. But anyway, so but we have data go way back. There's one right here. No, I'm just kidding. But of course, it's hard to calibrate these to know what it means. But this was coming from Baghdad, so that far south. Okay, the medium that connects the sun and the earth, called the solar wind. You probably have heard of that. The two people usually credited with inventing or postulating that, Gene Parker back in 58 and Ludwig Biermann in 51. Biermann noticed that comet tails always point away from the sun. This has been known for a long time. So here's another picture. And the iron tail of the comets usually points straight away. The dust tail kind of follows the orbit a little bit. And there are knots. The iron tail is not completely uniform. There are knots in that, and they move outwards. And Ludwig Biermann computed that the outward speed was about 400 kilometers per second. So, and since the iron tail is there all the time, the solar wind has to be blowing all the time. Parker's approach was different. He simply said the corona is extremely hot. Anything that hot will expand. And since it is there all the time, it means it expands all the time. So we are immersed in that solar wind all the time. Another thing that Wilcox and Ness somewhat later discovered was that the magnetic field in the solar wind, dragged out from the sun, does not point in random directions. For a week or so it would be pointing outwards, and for the next week pointing inwards, and then outwards, and inwards, so kind of a sectorial division of that. And that was quite a surprise. All right. So there's a little movie that shows what the solar wind can do. There's a comet. Oops. Did you see the solar wind blast stealing the tail of the comet? There it comes. Poof. Now that happens all the time. So here is a comet Morehouse in 1908. Halley's comet had the same problem. These are on 3 consecutive days, so you can see how it moves. Now this looks very impressive, of course, but the tail, the iron tail, is actually extremely tenuous. If you compressed the iron tail of an average comet to the density of water, it would fit in a small suitcase. So that it looks impressive. Huh? Now, one thing we must remember is that the electromagnetic force is 10 to the 38, 39 times stronger than gravity, so it's extremely strong, and therefore just a little bit of separation between the ions and the electrons can have a large effect. We'll come to that in a second. All right. We talked about magnetic field of the sun, and here is one of those active regions. Remember the black and the white bubbling up, and we can measure that. We can make a map of that. This is a map of the disk of the sun. If you take out the central strip, put one here, and then make another one tomorrow, put next to it. Of course, of one solar rotation, we have 27 of those stringed together. Then we can figure out where the boundary between the outward and the inward fields are. And it usually has this kind of strange shape, like a seam of a baseball. All right. And if we extrapolate that shape out into space, this is what it looks like. So here's Jupiter. The Earth is somewhere in here. That's a strange double spiral. And when the Earth is, or the satellite, is above this surface, of course, there is no surface, it's not purple now, right? But when the Earth is above that, we sample the magnetic field coming from the northern pole of the Sun. And if we're below, we sample the magnetic field coming from the southern pole of the Sun. Here's another look at that. So here we have the Sun in the middle, and that sinusoidal boundary, as the Sun is rotating, will mean that the solar wind will escape in that peculiar pattern and move out. One here is the speed, and the other one is the density. So you get a sequence of barriers. And the latitudinal extent of that depends on where you are in the sunspot cycle. So here's a little movie of that, a little graph of that. At solar minimum, this whole thing is very flat. And then when we get closer to maximum, it increases in size and completely goes around the Sun like that. And then after maximum, it shrinks again, becomes flat, and it starts again. So we have this oscillation between flat and filling the whole space. Now, why is that important? It's important because, well, here, before I say that, here's a cross-section between, similar to that. So we cut through Sun in the middle. We have this current sheet here. We cut a section, a meridional section through that. And at solar maximum, these undulations here go to very high latitude, and at solar minimum, they are very flat. Okay, now what does that mean? That means that when a cosmic ray from the galaxy, it's a charged particle, when it comes in here, it has a fair chance of meeting at maximum and meeting one of those. Each of these is really a bunched up, tangled piece of plasma, because the solar wind has different speed at different places. So the fast ones will catch up with the slow ones and will compress them. So this is really just means a set of compressional boundaries, if you like. And they tend to scatter charged particles, so cosmic rays will come in, bounce right back out again. If it comes in here at the solar minimum, it can get into the inner solar system, in here where we are. Here's another cartoon of that. So the amount of cosmic rays that reaches us depends on where we are in the solar cycle, and depends on the extent in latitude of those compressional barriers. And the primary cosmic ray comes in and hits an oxygen or nitrogen atom. It can basically destroy it, knock things out of it. And so in the process, we get created carbon-14, which is radioactive, or beryllium-10 is another one. Now, the amount of stuff we get created is very small. Global, over the whole Earth, in 1 year, 55 grams, that's 2 ounces, of beryllium-10 is generated. Not much. And 8 kilograms, 17 pounds, I think, or something like that, of carbon-14. And that, of course, you have to spread over the whole Earth. Carbon-14, of course, becomes carbon dioxide and taken up by plants and trees, can be found in tree rings. This is well known, you all know about that dating method. Beryllium-10 is metal, and it rains out. Basically, it's scooped up by rain or falling snow, and so accumulates where there's ice. It also hits right here, but it seeps into the ground and you can't find it. On the ice in Greenland and in Antarctica, it stays put. We can go and look at it. And that we do. So here are various places where people have drilled through the ice and gotten the core out, usually 10,000 feet long. And my daughter-in-law is one of those people. It's not one of those, but she's somewhere over here, and is doing this. And so then we cut this core into little slices. By the way, there are layers in that. So like here, each one of those correspond to a year, so we can count how many there are, so we can date each little slice. And we take that slice, we melt it, we put it in this big machine. This is in Switzerland. If you look real carefully, there's a person standing here. So it takes such a big machine to count one atom of beryllium-10. And with that, we can then make a record of the amount of beryllium-10 going back 10,000 years. So this is 9,000 here, 8,000, 7,000, 6,000. And it goes up and down, of course. So that, if we can invert that, is the right way, is a measure of cosmic rays. And therefore a measure of the sun's magnetic field. But not totally. Because the beryllium-10 we see in Greenland may not be created in Greenland. It may be created at lower latitude and brought up there by atmospheric circulation. So the climate or the weather also determines. So this is a convolution of the climate and the sun. And so we have to separate those two, which is difficult to do. And we don't really know how to be honest. So, another way of looking at this was invented by old friend Gauss and his companion Weber back in the 1830s. Namely a magnetometer. And here's one of the early ones. It's a huge magnet here, about 6 feet long. It's hanging in a thin thread here, and there's a mirror on it, and a scale, and a telescope, and so on. So you can follow how it moves. Later on, they got a little bit smarter. Not soon after that, it started in 1844 here in Helsinki, in Finland. This was very tedious. These people actually made an eye reading of that every 5 minutes during that time. It was usually done by graduate students. So at the observatory there was a director, and then it was sleeping quarters for 12 graduate students, right? So that was their job. And it was digitized about a decade ago, because it's never been worked on before. The result were in a stack of notebooks this tall. So my colleagues in Finland were smart. They took one notebook and sent it to one school, another notebook to another school. So this is your science project. Type all this in, send me this floppy back. Right? And over summer he got all that. So now we have that very valuable set of data. But people soon figured out that we can use photography, which has just been invented. So we have here a rotating drum with paper, photographic paper, and then a mirror here and a lamp. And then when the magnet wiggles, then the mirror will wiggle and we get a trace here. And that was actually used for almost 100 years. So here the same instrument. We usually have 3 to measure the magnetic fields in 3 directions. Right? 3 is a vector, so we need 3 values of that. Here's the modern one. It has no magnets, it has no mirrors, no photographic paper. It's all done electronically. It's a flux gate, 3 flux gate magnetometers in there, and a Newton magnetometer. And it all sent by a cable to a PC, and so none of this. However, that one here, this method was used up to about 10 years ago in some places. And that is what I grew up with. I learned how to use those. I don't know how these works actually. I do, but it's complicated. So we saw the Carrington event, 2 flare brightness here. So here's the magnetometer from Greenwich and Kew in England from that time, and you can see. Well, there is a problem with this, of course. Once the agitation gets big enough, the trace goes off the end of the paper and it saturates and it's lost. You don't know how big it was. But we do have these going back that far. Steve mentioned here that, or Scott mentioned that I actually did my studies about here. And the main issue I was studying was the magnetism of the Earth. And the first scientific description of that was given by Gilbert here, who was a personal physician of Elizabeth I. And he said the Earth is a great magnet. He had some of the field lines, and he even drew, this is not his drawing, this is our drawing, but he drew a similar one showing what he thought they should look like. So as a student, I was sent up to Greenland, right here, to observe the field. I had to build my own observing hut. This is the one that I built here. I built two. The first one collapsed. There are very simple rules for that. The blocks of ice or snow that you cut out has to have a certain size. We cut in a certain way, and I cut corners, so to speak. I made mine too small. And so once you were 2/3 up, just like that. But eventually I got it right. And basically, my dissertation was based on that, and interested Stanford so much that they invited me to come over, and I did. Now, you may wonder, how does one get there? Oh, before we get to that, I'm thinking, yeah, we're on the right track. So, what we discovered was that up here in northern Greenland, if you make a graph of the magnetic field during the day, it has a certain variation, and it's always the same for several days in a row. Then all of a sudden it changes to be the opposite. So what goes down, up, now it goes down. And at a station down here near the South Pole called Vostok, a Soviet station, it's exactly the opposite. So what we discovered there was that whether or not it went this way or that way depended on the polarity of the magnetic field in the solar wind. I plotted that here. So here's basically during 2002, a plot of the magnetic field in the solar wind, and you can see it goes like that. It's because the sun is rotating, so you get every 27 days like this. And at Thule up here, that's what the sign deduced from the magnetograms look like. And at Vostok look like that. And the effect is largest in the summer, and you can see it matches perfectly during summer, and it's very small during the winter. That shows that the Earth's magnetic field and the Sun's magnetic field are connected at all times. And that was at that time a big issue, a debate. Was the magnetosphere open or was it closed? Open means that the Sun's magnetic field and the Earth's magnetic field were connected. Closed means that there is a boundary, magnetopause, which separates the two magnetic regimes, so they don't have anything to do with one another. This was part of the clue that told us that this magnetic field is open. All right, so how do we get to the ice? This is how one does it. Hercules C-130 with skis. And to take off, we have some rockets here. It didn't always work, but most of the time, 9 out of 10, it worked. So now and then it looked like that. Now, why did we have that station up there? Well, it was in 1967. It was during the Cold War, so it was a good place to detect Chinese atomic bomb explosions. It's what really paid for this thing. All right, that was just a personal note. But of course, we can also count sunspots. That's maybe a more direct measure of the sun's magnetic field. And here are some drawings. This is the first drawing we know of from John Augusta in 1128. Claims there were 2 big spots. Galileo is well known. He was not the first actually that used the telescope, but he's best known. Here's one of his drawings. Here's Galileo himself. here's this telescope. They still exist, both of them. And I tried last year to use them in an experiment. They're kept in Florence in Italy, but they wouldn't let me. But anyway, here is again just showing solar maximum, sunspot there. Solar minimum, no spots. Rudolf Wolf, a Swiss, was the first to organize the counting of sunspots, and he discovered that there was an 11-year period, and this is the telescope that he used. That also obviously still exists and is used to this very day. Why that? Well, so we can calibrate, compare. And in fact, solar observers on purpose use small telescopes. All right. So, but before we get to the result of this, we should ask us, where does that magnetized solar wind come from? And so from the ice in Greenland, I went to Stanford, and we built this Wilcox. It was then called the Stanford Solar Observatory. And then John Wilcox died, an accident. So we renamed it to the Wilcox Solar Observatory, and it still exists. It's still taking data as we speak. And we started here in '75. Here's a map we made of the solar surface. But our predecessors down at Mount Wilson in Pasadena, Los Angeles, started in 1912. Here's one of their maps. And if you look real careful, here's a person in a basket. Goes up. They call it an elevator, but basically it's just a handrail and a place to put your feet, and then you go up. It was built by Otis, and it's been running ever since 1912, and it's very reliable. But of course, in the steel bar, which is the handrail, many famous people's fingerprint are engraved in there. Of course, it's a very scary thing. It doesn't stop. It goes in a continuous bed, so you have to jump off and jump on. Anyway, now we have our Solar Dynamics Observatory, as I mentioned. Here it sits just over New Mexico, and here's the launch of that, and you can't see it, but there's a person standing here. But this is really just a continuous evolution, and measuring the same thing. And one of the problems we have here is to connect those, to calibrate them so that the early measurements make sense. And we managed to do that. So, back to Rudolf Wolf, who lived here, and his sunspot cycle. So, remember this pattern here, which separated the one polarity from the other polarity. And along this boundary, we often find active regions, sunspots. And this is what Wolf counted. We number these cycles. There's the first one, number one, 2, 3, 4, 5. And there seems to, each one of those here is 100 years long, 110 years. So there seemed to be sort of a 100-year period in that. And here we are today. We had a big one here, and then it had become smaller and smaller, and that one is not too big. So the interesting thing is, what will it be in the future? Can we predict it? Can we play this guy here? So what we do also as a byproduct of our observations at Wilcox is we measure the polar fields of the sun. That is in this region here near the North Pole and near the South Pole. And why the polar fields? Well, there's a little movie here that should be running. There's a circulation in the sun, just as there is in the Earth's atmosphere from the equator to the poles. For the same reason, probably, there's a temperature difference, not large, maybe 3 degrees or so. And this circulation brings up the magnetic field from decaying sunspots. And once they reach the pole, of course, they can't get any further, and they don't pile up indefinitely, so they eventually are advected down. I say advected because we don't know what that means, but that's just a fancy way of saying that since they don't pile up, somehow they must make it down to the bottom. And down there, this circulation must close, otherwise we get everything up at the North Pole. So during the trip back here, we have the same thing as I talked about in the beginning. We have conducting plasma moving across the magnetic field, which the polar fields. That induces a current which has a magnetic field of its own, which amplifies this thing, and then you have more plasma move through a stronger magnetic field, you amplify it further, and so on, so on. So the net effect is that you create sunspots out of that, and they rise to the surface in about a month or so. Come down here, and then they decay, and the decay products go up here, go back in, and so this thing cycles, takes 11 years to go around. So the polar fields seem to us, like 40 years ago when we first thought of that, to be a predictor, because if they're strong up here, then it stands to reason that there will be more spots, because the dynamo mechanism there has more material to work with. So we said that, okay, if we plot the polar fields as a function of time, that should be able to should give us a mean of predicting what the next cycle is going to be. So here's what we've done here. So this is the strength of the polar fields. It doesn't matter what the units are, at Mount Wilson and at Wilcox, and it goes like that. There's clearly a 11-year cycle. The interesting thing is that the polar fields go through zero at every maximum. Why is that? Well, that's because there were the old polar fields from the previous cycle, and now comes the new polar fields, and they have the opposite polarity. They cancel out the old, so they go away, and then continue to build up a new one. And then at solar minimum, here, here, and here, the polar fields are strongest. I kind of just inverted this just to show you an easier way of comparing them. And this has been decreasing for the last 4 cycles or so. Here's the sunspot number of sunspots, been decreasing as well. So some years ago, almost a decade ago, NASA put up a panel to try to predict the sunspot number. Why is that important? Well, the sunspots, solar storms, can damage satellites, for example. And many people, remember there were 650 satellites out there at geostationary orbits. If you are a commercial satellite company, then you send up these things, but they cost money, $500 million each. So you go to a bank and you loan that money. Now, when you loan something to a bank, you've got to have insurance, your mortgage and so on, right? Now, what shall the premium be? That depends on how many sunspots there are going to be over the lifetime of the satellite, the next 10, 15 years. So the insurance companies goes to the government and say, how many spots are we going to have in the next cycle? The government says, I don't know. So they ask us what we think. Right? And so here's the panel. This is me. Since it had to fit in this one, I had to use Photoshop to shrink it a little bit so we look at suitably thin and nice here, right? So anyway, we predicted a small cycle because of that. So how are we doing? We're doing good. This is the prediction is here, this thing. All right? Now, we published that paper here in October 2004, almost 10 years ago. Of course, the insurance companies, they don't really care what the number is. They just want to say, don't complain about the premium. The government gave us those numbers, right? So, and I'm really not kidding. It is the insurance industry that has prodded the government to make those predictions. But so far, we're doing good. And that probably means that we have this thing, we have understood, at least in gross details, how this thing works. All right. So the sun is variable. So is that a cause of climate variation? One would tend to think so. Many people think so. But it's not. the course of the large variation. So I have here several panels with of increasing length of years. So this is the last 160 years. And what is shown here is basically the temperature. And here's the famous global warming, and so on. And here's the past 2,000 years. So we have warming here, and something down here called the Little Ice Age, where it was cold. People were having ice fairs on the Thames in London, and the Dutch were having making paintings of snow-covered villages and so on. And so that thing here is really this thing. And then here's the past 10,000 years. And it has been cooling the past 10,000 years, as you can see. Here's the past 100,000 years. And so here's the 10,000 years we're talking about, called the interglacial, this warm ice age that just ended. Here we had the glaciation, where it was considerably colder. And interesting enough, if you go back to the past almost million years, remember each of these boxes contained the previous panel. So then we see there's a definite systematic pattern to that. And we think we know why that is. That has nothing to do with the sun. This is caused by Jupiter. How is that possible? Well, Jupiter is one of the biggest planets, and it changes the shape of the Earth's orbit. And one can, if, excuse me, if in the northern hemisphere, where we have land, where snow can accumulate, if we are furthest away from the sun in winter, then there's a bigger chance that we'll get more snow. And so one can simply calculate what is the so-called solar insolation, what is the amount of sunshine we get up in northern Siberia and in northern Canada. That matches that curve pretty well. Go back 2.5 million years. Here, that now is something else that comes into play. That is the tilt of the Earth's axis that also changes due to Saturn, basically. And so we have a slightly different periodicity. Go back 500 million years, see that this time here is where we have those glaciations. Before that, we didn't. Why is that? That's probably because more than 50 million years ago, Siberia wasn't where it is now. So we didn't have all that land up north, right? And so on. So we go back 500 million years, there was another period of glaciation here because the continents were all together, so we had glaciation in the south. Of course, none of this has anything to do with solar activity. That's the Earth's orbit modulated by where Jupiter and Saturn is. But certainly we could say, well, on a shorter term, it must be controlled by the sun. After all our energy comes from the sun, right? And the usual stupid comment people make, well, try to turn off the sun and see what you get, right? If you doubt that the sun is important. That's of course nonsense, but it's an argument you hear. So here's the last 2,000 years, I think. No, last 10,000 years. So here's modern day, a little ice age dip here. And so here's the interglacial just after the ice age. This is from Taylor Dome in Antarctica. And it's been cooling, as I said, ever since. And we are on the way to the next ice age. We'll come in another 40,000 years. Slowly down. Nothing we can do about that. And if we blow this thing up, we have our beryllium cosmic ray record. But there is very little correlation between this and that. So there's very little evidence for that. All right. So another argument is, well, was the little ice age global? Was it just something local? And my answer to that is a poem by a Danish poet here. You can see for yourself what he had to say about that. So I guess the general opinion is that the little ice age was global. So And that, we're almost done now, comes back to, okay, so we get something from the sun. We're measuring something called the total solar irradiance. That is the total amount of energy that we get from the sun. And we can measure that. We'll see it in the next slide how we do that. And there's a simple formula here between the change in temperature and the change in irradiance. This is basically Stefan Boltzmann's law in reverse. It counts for the quarter here. Right? So if we could change this thing, solar irradiance, by 1%, that means the temperature will change by 0.25% times T, which is in Kelvin. That comes to 1 degree centigrade. So if we could get the sun to vary by 1%, we'll get a temperature variation of 1 degree. And that's enough to cause the little ice age. And Jack Eddy here, late Jack Eddy, my good friend, back in the 70s proposed that there was a connection there. Because at the time it was thought that a variation of the solar irradiance of 1% was very plausible. Okay. George Sweetie Abbott had measured that in the first part of the 20th century. He was a director of the Smithsonian Institute, and he put up stations all over the world on top of Mount Whitney, in Peru, 2 other places, and thought he could see a 1% change with the solar cycle. So that was, at the time, sort of reasonable. I have an anecdote about Abbott. Was a sun, weather, climate conference at NASA in 1973, which I attended. And Abbott was at that time 101 years old, and he gave the keynote speech, and he died the next day. But work done. What a wonderful man. The keynote speech with no fluttering, very, very clear. His voice was as firm as mine, although I'm 30 years younger. Anyway, so this is a classical thing here. Stuff coming in, reflected back out, absorbed, going back out, and so on. You've probably all seen things like that. And we don't, some of those numbers here are somewhat uncertain, but once we are on the level of 1%, these numbers are hard to get at. But it all hinges on this guy varying. And finally, in 78, back here, we got the first satellite up to measure that. And well, the way we do that is we have what we call a active cavity. There's a little thing like that. It's no bigger than my thumb, in fact. And it's painted black on the inside. And we just let sunlight fall into it. Boom. We have several of them, so we can compare them. And of course, if sunlight falls on this black surface, it heats it up. We wind an electrical wire around that. So we heat up, we adjust the current in that wire such that the temperature of this is constant. That means that the amount of current is a measure really of how much sunlight comes in. That's how we measure this. And that started back here in 78. And these are what different satellites gave, and they're all over the map. They do, however, overlap, so one can calibrate them between each other, and this is the recent calibration. And it shows here for those 4 cycles that the variation is not 1%, it's 0.1%. That means, going back to the formula from before, that the variation we can expect is not 1 degree, but 0.1 degree. And that does not explain anything. And by the way, this one also usually strikes people. We have a much bigger variation through the year because of the varying distance between the sun and the Earth. 7, and that's squared, because radiation falls off with a square. So we have a 7% different. So here we stack 12 years of data on top of one another. And all 12 years are plotted, of course. They follow very closely the same curve because the Earth orbit is very stable. And now and then you see a teeny tiny little wiggle. That's solar activity. That's the sunspots. It's hard looking at this one to believe that those things can do much, and they don't. Okay, a way out of that is to postulate that, well, maybe, so here's the the measurements that were made. And we can people have tried to reconstruct what this TSI curve looked back in time using the sunspot number as input. And that, of course, doesn't do much because it doesn't vary much. It doesn't vary a tenth of a percent. So they say, well, maybe there's a slowly varying background underneath that this 1/10% sits on top of. And then by varying the background enough, we can get any variation that you like. The current opinion is that there is no such background. And so that excuse probably doesn't work. So, the conclusion I will draw of this is that any solar activity influence must be small, and therefore not relevant to the climate debate. Now, that doesn't mean that everybody agrees with that. So the debate continues. So here's from Washington Times a few months ago. One scientist that shows this graph, the black one here is solar radiation, he claims. And the gray one is the daytime temperature in the contiguous US. And he says, see, they're matched. The sun is doing it. No, because what he's done here, he picked one reconstruction that happens to match this temperature from that portion of the globe. So by cherry picking enough, you can always find something that works. I would call the modern view on the variation of TSI is given by this red curve, and there's not much correlation there. On the other hand, this is a vigorous debate. Yeah, we need more data, more funding. Get that one? So it's very exciting to be a solar physicist today. That was it. Thank you.